Okay, so we should be live, and welcome to another live stream from the Assumption of Physics. Today we have a guest, Ariel Caticha, who is going to talk to us on his work on the foundation of physics and quantum mechanics, linking essentially the dynamics with entropic inference. And it's very similar. Some stuff are very similar to stuff that we do and we have talked about. And it's interesting to see how his different perspective comes to sort of very similar results to what we have. And so this is a very good opportunity to sort of exchange idea and work with each other. And the reason we're doing this live is because we have been in contact from time to time and chatting, and I have some open questions that I wanted to ask him. And so I said, why don't we do it in front of everybody so that everybody can learn about things. For today, I don't know why I have the captioning on from Zoom. I don't know how to disable when it's turned on. And so we'll get this thing, and I'll turn it out to Ariel. Please, Ariel.
Well, hello. I'm so glad to have this opportunity to show my work. Thank you very much for the invitation. Looking forward to the discussions. Maybe I should give a short background on my own history. Okay, born in Uruguay, so my native language is Spanish. Grew up in Brazil, so my almost native language is Portuguese. I have been living in the United States for the last 10 decades. I mean, like forever.
So how old were you when you came?
I came for my PhD.
Oh, for your PhD.
Yeah. And then I went back to Brazil, but then I came back again. So I've been here like for 40 years or something like that. I'm as American as it gets at this point. Yeah.
Okay.
Anyway, I was always interested in foundations of physics. And at some point, I realized that if you wanted to do quantum gravity, that's the ultimate goal that was given by fate to our generation, right? The big problem lying in the background, quantum gravity. That in order to do quantum gravity, if the problem were quantum field theory, then Weinberg and Feynman and Gelman would have done the problem, right? On the other hand, if the issue had to do with doing general relativity better, then Penrose and Thorne and so many of these other guys would have done it. So obviously there was it's something else that's the problem, right? Yeah. And I realized that the only problem where you can do quantum gravity, or rather, you can put quantum mechanics and gravity with any sort of reliability. You can put them together. Is the problem of black hole thermodynamics, right? And Hawking had done something along the line, those lines. So I thought that the best way to do this was to learn a little bit more about entropy, right? And one of the things that started to strike me as general is that everybody who was invested in doing fundamental physics, all the educational programs that deal with fundamental physics have very lousy courses on statistical mechanics and on the notion of entropy, right? And so I decided that what I was going to do when I got when I got to a tenure track position, which is like 35 years ago, what I was going to do was precisely teach statistical mechanics so that I could learn that properly. In doing so, I came across the work of Edwin James, which changed my life forever. I'm not saying that James was correct and right in everything that he did. No, he didn't. But he did take the most crucial steps in the direction of understanding or understanding probability and understanding entropy. And so I thought that I could take as a goal for my career, once you have tenure, life becomes nice, right? You still have to deal with deans and provosts, but you are the owner of your own nose. So that's actually very useful. So I decided that I would take as my career to do for quantum mechanics what James had done for statistical mechanics. And it's worked out. The progress is very slow. It's taken many, many years. But it's working.
Yeah. So I think probably it's one of the reasons why we click so well. Like as you know, my background is I come from engineering side. In fact, the software engineering side, informatica. And I did study information theory well. And then when I went and talked more to physicists, I realized that they have like a poor understanding of information theory and that stuff. And I do agree when I was reading Jane, he was able to put some things together, though some things are not quite in the right way, but at least he made a lot of right connections. So.
That's right. His ideas about quantum mechanics were not correct. He didn't make that leap properly, but he did take a few steps in the correct direction with the connection between information and entropy, based on previous work by Shannon and other people, but also including Bayesian probability theory in the mix, and not the orthodox subjective Bayesian probability theory. This is more like an objective probability theory. Objective not being ontic and real, but rather objective. We all agree what, you don't get to have any opinion.
You always get the same result, and we all agree. So that's the part that I think James didn't, like I think he had the right idea in his head, but when he wrote him down in paper, sometimes he used the language that completely threw off a lot of people. But the examples were always clear.
Oh, yes. Maybe one thing that I should say during my talk later, but maybe I should just say it right now. There is a confusion that takes the dichotomy of subjective objective as being the same as ontic epistemic. Ontic epistemic is not the same as subjective objective, right? So probabilities in quantum mechanics are epistemic.
Yes.
But they're objective. You compute any other probability, you're going to be wrong. It's not going to agree with experiment. So they're objective and epistemic.
And the confusion is that you can use the same tools of entropy and probability to characterize things that are subjective, but the fact that you can use the same tools, it doesn't mean that they're always subjective or they're always objective. Vehement agreement. Yes.
Yeah, and playing with the words, the right words, paying attention to the way you use your words is extremely important, because words are the only tools we have. So anyway,
let's get started. Please share the slides and see if everything.
Let me see if I share the correct one. Let me see. How is that? Is that okay?
You're sharing. I see the PowerPoint window. Can you try to make it full screen and see? Yes. No, we see the wrong screen.
Oh, okay. Let me try again.
Yep. Sorry for the technical problems.
No, that's yeah.
I'm talking to the other. Okay, we're good.
Is that better?
Yeah, that's perfect.
Okay. It's always a matter of trial and error, mostly error, right? Yes. So the subject for the talk is going to be reconstructing quantum mechanics from symplectic and information geometry. I first have to acknowledge all the people that have collaborated with me over the years. Most of these guys have been my students. My current students are the ones indicated in blue, and they're dealing with topics such as quantum field theory, the classical limit of mesoscopic particles. In fact, Gabriele, you have a paper in which you talk about the classical limit as
Yes.
being the classical limit refers to mesoscopic particles with a large number of particles, right? Large n. That's exactly what Fatima is doing.
I actually have a paper right now that says that it's the limits of large entropy. So if you take any space and you look at the mixed states with high entropy, they look more and more classical. So that
I believe you. And then Keegan is working on the problem of particles with spin,
okay.
which is an interesting twist in its own.
Yeah, I have questions on relativistic spin as well. So yeah, anyway, we'll probably, make more of these sessions throughout
Okay,
the
very good. So the presentation here, there are many papers on this, and here I'm giving you the archive codes. The presentation here is based on this paper of 2021. But much more stuff can be found at my webpage, arielcaticha.com. There you can find lectures and videos and papers and stuff.
And your book. So this is another
Yes,
thing where
yes,
we are similar, that we are both like putting all our knowledge and all the results in a book that it's open access and that people can go and look. So that's
absolutely.
another thing that we do very similarly.
Absolutely. There is a draft of my book. It evolved from my lectures and lectures on information physics. There is a draft there, and I am planning to put a major update with additional chapters and stuff within a month or so. Very good. So the subject is quantum mechanics, the goal to derive or reconstruct the mathematical formalism. And in the traditional approach, the Hilbert space comes first. People always start with a Hilbert space. But then there are a bunch of questions one can ask, like, why do you have probabilities? Why do you have quantum probabilities? Why do you have a Born rule? Where do all those things come from? Why do you have two modes of evolution of the wave function, like a linear unitary Schrodinger evolution, and then you have wave function collapse? So you have a bunch of questions that have lingered over the years, and people have given lots of answers to these things. Perhaps the most basic question is, okay, you have quantum mechanics. What's real? What's ontic? What's epistemic there? How do you interpret the whole thing? An alternative approach, and this is what I'm going to follow here, is that probability comes first. You do not have to explain why you are uncertain. Uncertainty is the natural situation in the world because you don't have enough information. So maybe you have to explain why you might have certainty. in some cases, right? So the alternative is probability comes first. There you have to, okay, if I say probability comes first, then the probability of what? That's a crucial part of the whole thing. And there you have to answer other questions. How do wave functions arise? Why do you have complex numbers? Why is the evolution of probabilities eventually given by a linear equation? Why do you have a superposition principle in the first place? Where do Hilbert spaces come from? So the questions are completely different here. So let me explain a little bit the logic behind reconstruction. The issue of the interpretation versus the formalism. And this is actually the major strategy that one follows in order to make progress on this business of quantum mechanics. The idea is, in the traditional approach, one starts with a given mathematical formalism, Hilbert spaces, linear algebra, all that. And then you append an interpretation to it. Just try to figure out what the various symbols mean. And the issue is that you can put many interpretations. Copenhagen, many worlds, Bohmian. You can you have a variety of interpretations there. And the issue is, which one do you choose? How do you proceed there? the alternative is the following. Now, we notice that these many interpretations deal with the subject matter of quantum mechanics, so what quantum mechanics is all about. So what I'm going to do is I'm going to start by deciding what quantum mechanics is all about. I start from there, and then I try to derive, making various assumptions, I try to derive or reconstruct the various possible mathematical formalisms.
Yeah.
You have to make assumptions. Different assumptions lead to different formalisms. Now the question is, wait a minute, isn't this just as bad as the previous one? Don't you have a problem here? How do you pick? Well, here we have the advantage that it is the mathematical formalisms that produce data that we can compare to experiment. So now we can have experiment to help us decide which one of these is the one that works. And you pick the one that agrees with experiment. It turns out that the one that agrees with experiment is, of course, the one that people had figured out before that works pretty well. So this is the logic. We start with a clear idea of what we're talking about. We make reasonable assumptions. And from there, we derive a mathematical formalism. In the end, we know exactly what the mathematical formalism means because we started from something we understand. Now, this is a framework. Depending on what I think the theory is about, we can have, for example, the theory being about particles and derive a non-relativistic quantum mechanics. But we could start with fields, and we can adopt assumptions that allow us to derive the formalism of quantum field theory. So the framework can be applied, the whole logic can be applied to quite a wide variety of physical systems. I'm going to do that. I'll start with the kinematics. You'll see what I mean by this. But I'm going to start by imposing what I just said, ontological clarity. We have to ask what's real here, what are we talking about, what's epistemic. So I'm going to start with discrete ontic microstates because that's very simple. I won't have to deal with functional derivatives. It's going to be partial derivatives. So for the purposes of explaining what I'm doing, this is enough. So I'm going to start with an n-sided quantum die. You have n possible microstates. We do not know what the microstate is, so we have probabilities. Here is the probability of phase j, which I'm going to write as rho with an upper script j. And this should start to indicate the way that this is going to go. The fact that I put a sub upper script j here is because at some point I'm going to be doing differential geometry, right? The geometry is going to be, this is part of the assumption.
Yeah, these are coordinates.
Yeah. Yeah. So rho is going to be a coordinate here. Now, these probabilities are Bayesian. Whole subject of discussion. What do we mean by that? Anyway, they're Bayesian, but they're not personalistic. This is crucial, right? If you compute these probabilities according to your own feelings, you're going to get the wrong answers. You better compute the right probabilities. So these are very objective. Oops, what happened here?
Nothing. The screen.
Oh, there. Okay, I just clicked on the wrong thing. All right. So here, the Bayesian probabilities, they're not personalistic, and they're definitely not quantum probabilities. They're standard probabilities. I take the position that probability theory is of universal applicability. They're tools for reasoning. So our goal here is going to study curves on the n-1 dimensional simplex of probabilities, the space of these probability distributions, the space of all probabilities that are positive and add up to 1. So we want to study curves that are interesting curves in this space that sort of like accommodate the structures that are available in this type of spaces. So that's why this is only a kinematical prelude to the actual dynamics. So I'm going to disappoint you, perhaps, Gabriele, in that I'm not going to be doing dynamics. This is just kinematics. But I have a reason for doing this. The reason is that the kinematics is what's going to lead us to everything we understand as quantum mechanics, basically the Schrödinger equation and all that. Then there is the issue of how do you pick the Hamiltonian? What do you mean by time? That's the actual dynamics. And if I had another hour to talk about it, or maybe another half hour, I would be able to tackle that. But I won't get on all the way to that.
Yeah, to me, the important is that we give the audience a sort of a general sense of how this works, right? So,
okay, yes, I can bring that at the end.
Right. And then, if people are interested, to know more, you can leave a comment and we can organize another session.
That would be ideal. Yes. So here we go. This is we're going to study the basic, the curves that are interesting in this space. So here you have a little picture of a simplex so that people have some idea in their minds what is going to be happening. These are the normalized probability distributions. This looks like a plane, but it's not. The geometry of this space is actually that of a sphere, which is absolutely crucial to get quantum mechanics. So here we go, some geometry. This is again so that you have a picture in your mind of what the mathematics is going to mean. So here you have a simplex in n-1 dimensions. There is a probability distribution. It is a point in this space. This is a statistical manifold, a point there, call it rho. We're going to be, and oh yes, and this simplex is going to be the epistemic configuration space. It's a good idea to keep in mind that we have an ontic configuration space, which is basically the n faces of the die. It's discrete, n points. That's the ontic configuration space. And we have the epistemic configuration space, which is the set of probabilities on that ontic configuration space. So here is the epistemic configuration space. We're interested in curves here. These are going to be candidates for trajectories. Mm-hmm. A vector here, a tangent vector, is going to be a velocity. And so here I'm going to put the tangent space with all possible velocity vectors. I call it velocity, but tau need not be time. It could be, for example, what happens when you do rotations on this space. And if you do rotations, the tau could be an angle. So how do things change when you do some sort of operation on the probability distributions? It's going to be described as some parameters. Sometimes the parameter may be angles, it may be for translations, or it may be translations in time, and that's the one that will give you the dynamics. Anyway, so very good.
So just to clarify, so we said that the points to which you assign the probability, those you're calling the ontic states.
Yes.
And a specific probability distribution is an epistemic state.
That's right. That's right. So the natural question to ask is, I deal with probabilities. The obvious question to ask immediately is probability of what? What is the probability you're talking about, right? And I'm talking about this n discrete ontic states, the possible faces of a die, for example. Yeah. Anyway, this is the tangent space at the point rho. If you put tangent spaces at every point on this base space, you get a tangent bundle. Very good. So that's that. Now, in addition to curves, you can also put functions on the space. And you may be interested in talking about, say, gradients of the functions. I tried to draw here the level lines that define what the function is all about. At the point rho, you also have the space of all possible gradients of functions, the space of all possible covectors. I drew one there. This is going to be the cotangent space at the point rho. And if you consider the base space and all possible cotangent spaces at every point rho, you have the cotangent bundle. Now, why is this important? The reason this cotangent bundle is important is that, before we proceed, yes. So what are these covectors that you have up there? In classical mechanics, the possible covectors that you're going to write here are momenta. The possible velocities, the possible vectors that you write over there are velocities. The possible momenta, the possible covectors are momenta. Now, here in this approach, we don't have a Lagrangian.
Right.
We do have generalized coordinates, yes, the rows, but we do not have a Lagrangian. So we have to put something else here. In entropic dynamics, we're going to say that there is some kind of conjugate momentum, and the conjugate momentum is going to be some kind of function here. This is actually very important. I'm trying to decide, or I'm making assumptions about what are the variables that are going to enter into the whole mathematical framework.
Right.
And these functions that I'm going to put here are crucial because they involve or play three different roles. One role is going to be, these are covectors. They're going to be conjugate to the rows. One.
Mm-hmm.
Second, and this will be explored in this little talk. The second important role that this phi plays is that the rows will determine the magnitude of the wave function.
Yeah. Mm-hmm.
The wave function modulus squared is going to be rho. Yeah. We don't know that yet, but I'm just giving you some things, a preview of things to come, so that you don't get completely disappointed that this doesn't look like quantum mechanics, right? Mm-hmm. So this rho is going to be connected to the magnitude of the wave function, and this phi will be the phase of the wave function. So without talking about wave functions or phases or anything of the sort, we're going to set up a dynamics that already starts smelling like quantum mechanics.
Right. So if I understand correctly, this is sometimes called the S, so the thing that you put in the exponential. And it's also the thing that you use for a path integral type thing, right?
Yes, I think so. If you take classical limits and everything, this would be connected to the action, right?
Right. Exactly. Yeah.
Yeah.
Yeah. And the gradient of this probably is going to give you the probability flow when you do, for example, Madelung equation or Bohm type interpretation.
Yes. Oh, yeah. That's a comment that actually is interesting. Whenever we're trying to derive quantum mechanics or talk about quantum mechanics, of course, we have in mind something like a Schrödinger equation in the background. Mm-hmm. So no matter how you approach quantum mechanics, at some point, you have to agree about something with everybody else who's working in the field, because you know that the Schrödinger equation is basically correct, right?
Yeah.
So yes, of course, this will look like the Madelung equation. Yes, Hamilton-Jacobi equation, quantum potentials, the whole thing. Yes.
Right. Yeah. So this is also interesting because one of the things that we want to do in reverse physics and assumptions of physics is to show that all these sort of even how to go from all the different mathematical representation and show that all those things are equivalent and so on. So again, knowing already how to do it, it's important because with all these different sort of way of expressing quantum mechanics, you typically get different intuitions. And so then you can you know, oh, it's easier for this particular problem. This intuition is better, and this intuition is
Absolutely.
better.
We are scavengers. We are totally scavenging from other people's brilliant ideas. Yes.
It's exactly why I'm here, because I'm trying to see what pieces can I use to put
What
in
can you steal?
integration.
Please feel free to steal
Yeah,
everything.
exactly.
Yes.
Yeah,
Yeah.
yeah.
I said that there are three roles that this phi plays. One of them, it's a conjugate momentum. The second one is, I forget now.
The probabilities.
With the probability, the conjugate momentum to the probabilities. The other one, yes, it's a phase of the wave function.
Right.
Yes. And there is a third role that it plays. Eventually, this will be an entropic dynamics. If you want to update a probability using entropy, you need constraints.
Right.
Anyway, this quantity here will enter in the constraints that you use to update the probability distribution. And
yeah, okay, it would make sense because, as we said, in the Madelung equation, it tells you the flow of probability, so you're
the flow of
constraining the flow
probability.
of probability.
And the flow of probability is going to be given by a curve. That's going to be the Schrödinger equation.
Yeah.
And the updating from one point to the next in very tricky ways and everything is going to be obtained by maximizing an entropy for the transition probabilities. And these are going to be related to the constraints. So
You use so this is something that I don't appreciate. Okay, because so one of the things that I've always noticed is that you could see the sort of the measurement as an entropy maximization process. When you're doing the collapse, you can go to the mixed states that is mostly closer to the. And also the Schrödinger equation can be seen as infinitesimal projections so that you could see, so okay, we're in Riemann agreement here. I didn't even realize. Okay, cool.
This is very interesting. Okay, that's why one of the important ingredients in the theory of the whole theory of inference, one of the important ingredients that's necessary to do something like this is to recognize that updating probabilities using entropy and updating probabilities using Bayes' theorem are part of the same scheme. You need an approach that unifies entropic inference with Bayesian inference. And in order to make this thing work, because then measurements consist in discontinuous updates of the probability distribution.
Yeah.
When you obtain data, right?
Yeah.
On the other hand, the Schrödinger equation consists in continuous
updates. Yeah.
And if you're going to say you're doing inference, you can't say that these things are intrinsically that different. It's just different pieces of information induce different updates. That's all.
Yeah, because at the end of the day, it's all about what you can predict with the initial states. And so these probability updates are essentially the update on your prediction. And if you're deterministic and reversible, then all the information that you have at the beginning is exactly the same information that you have at the end. But in other cases, you might, if you're not deterministic, then you might have.
Exactly. Okay.
It's always so nice how we look at these things differently, but then we are in vehement agreement. It's always fascinating to me. Anyway, go ahead, because otherwise.
Okay, so now let me say that this cotangent bundle is the epistemic phase space. In the entropic dynamics approach, there is an epistemic configuration space and there is an epistemic phase space. There is an ontic configuration space, the phases of the die, the positions of a particle, things like that. These are the ontic configuration space. But there is no ontic phase space because the particles may have positions, but they don't have momenta. The objects that have a momentum here are the probabilities, not the particles. This is what allows entropic dynamics to claim that particles have definite positions, but they don't violate the uncertainty principle. So that's just food for thought for some other talk.
Okay.
Anyway, so some notation. A point in the phase space is given by rho phi. We are going to introduce an index here, alpha 1 or 2, depending on whether it is rho or phi, so that we can do differential geometry and all of those.
Okay.
vectors, covectors. Vector is going to be written this way, sum over repeated indices and all those things. The components of the vector are basically the velocity and, well, the time derivative, the tau derivative of these things. An important technicality is that probabilities, unlike generic coordinates, probabilities are normalized. So it's going to be much more easy to dwell with the space of unnormalized probabilities, a cone. Okay, yes, here I have a little trick here. Whenever you see a little red star here, is because there are comments that I ought to make, but I'm going to be very quick about them, right? In particular, the fact that it is so much more convenient to deal with unnormalized probabilities is what eventually leads to rays in Hilbert space. So Hilbert spaces are not really fundamental, they're not really necessary, but they are convenient. And the states that we use in quantum mechanics are not quite just the vectors of the Hilbert space, they're rays in Hilbert space. And that comes from the fact that it's much easier to deal with unnormalized probabilities.
So
anyway,
wait a second, I have a question. So the cotangent element, though, they're still going to point within the foliation of constant probability because the trajectories can't go.
Oh, very good.
Right.
Yes.
Yeah.
Oh, yes, yes, yes.
Okay.
In fact, if we're going to introduce one more generalized coordinate that basically is the normalization of the probability, right? The magnitude of the whole probability, then you also have to introduce one more conjugate momentum, right? And if you introduce one more, that means that you have unphysical elements playing a role in your theory. At some point, you're going to have to normalize the probabilities, so you get rid of 1 degree of freedom, and you declare the corresponding conjugate momentum. You can declare it unphysical.
Okay.
And this is going to be the phase of the wave function. You can modify the phase of the wave function by a constant amount, right? And that does not alter your inferences.
Yeah. So there is a question in the chat that I also was wondering. I was leaving for later, so now I'll ask it.
Yeah, sure.
So
yeah.
the integration then is not all the pure states, but just the eigenstates of a complete set of observables. That's the idea.
Let's okay. You're getting into the problem of measurement. What do you mean by measuring momentum? What do you mean by measuring this, measuring that?
Well, no, even beforehand. So
let me say that a point in phase space is a pure state. A point in phase space is a pure state.
Okay, a point in phase space is a pure state. Okay.
And you can see that from as a preview of things to come. If the rows tell you the magnitude and the phi's tell you the phases, then it's a pure state.
Okay, so if I have a spin system, then how? Okay, so for you, then it becomes a measurement question of what that thing is.
That's right. Yes.
Okay.
Yeah. In fact, I have slides for that, but
okay. So let's pause it and we'll discuss it later then.
Yeah. It works. I mean, it's let me.
Yeah. That's kind of why I said I'll ask this later, because I want to see where you're going and not disrupt the flow. Let's continue and we'll come back to this.
In the first slide, I said this talk is based on this four papers, but I only will talk about this one. One of them is precisely about the measurement problem.
Okay.
And how entropic dynamics evades all those no-go theorems that tell you that you cannot have realist psi-epistemic models. So that's a really important question, right? And you guys have papers on that as well.
Yeah, and I keep getting replies to papers that basically shows that the people making the reply didn't understand what the arguments were. It's like, I don't understand, Ariel. Like, to me, it's even things like, because they seem to be all these people that keep keep trying to use classical probability in the sense of putting the whole epistemic state inside a classical probability, right? And you probably would agree that that doesn't work because that's not how you're doing it. You're putting.
I'm using classical probability. In fact, I would object to the term classical probability because there is no classical probability versus quantum probability. There is a single probability, but you have to know what you're doing.
Right.
You have to know.
But again, for you, the epistemic state is the probability plus the S.
Yes.
So it's not just a probability. That's what I'm saying, right?
Oh, of course. Yes.
Right. It's not that the probability is not classical or quantum. In your mind, you have a classical probability P, but the epistemic is the probability plus
the conjugate momentum.
Exactly, plus the conjugate momentum. While on the other side, they're trying to cram both things in a standard probability setting, and that's the part that is not going to work.
And this is the crucial element. They're trying to reproduce quantum mechanics with what people call ontological models.
Yeah, exactly. Yeah.
Quantum mechanics is not an ontological model. The entropic dynamics that I'm developing here is not an ontological model.
Yep.
At some point we can discuss that too. Yes.
Yeah. And anyway, yes, that's great.
So now the symplectic geometry of the phase space. Basically, once you have rhos and phis, you can invent a symplectic form, a tensor like this. It's an antisymmetric tensor, and you can write it in terms of components for any when acting on any two vectors in phase space. You are going to have the components there. The components take the usual form that you expect of a symplectic tensor. It's antisymmetric like this.
So why does the nabla have a squiggle on top?
Oh, here, yes. Okay, very good question. It's because this is a gradient.
Yeah.
But it is not a gradient in the epistemic configuration space. It is a gradient in the full epistemic phase space.
Okay.
So these derivatives include derivatives in the rho variables.
Yeah.
And also derivatives in the phi variables.
Right.
If I go back here, like these derivatives here, include derivatives also in the phi. So this is really the differential geometry of the full phase space.
Yeah.
Anyway, so here we have this epistemic tensor. It defines a symplectic geometry. And the amazing thing about this, okay, this is where things start panning out. Why do I go through all this abstract stuff, right? The amazing thing here is that if you look at vector fields, you consider curves and you have their tangents. The vector fields such that the derivative of the omega tensor, the symplectic form, vanishes. So the directional derivative of omega along a particular field vanish. So those are very special flows. This is a Lie derivative, which is just a fancy version of a partial derivative in a curve space. So if you look for those special curves such that their tangents preserve the symplectic form in the sense that the Lie derivative vanish, those curves have a very special property. The very special property that they have is that by Poincaré's lemma, associated to a vector h that satisfies this. So if you move in the direction of the vector h and the Lie derivative of the symplectic form vanishes, associated to h, there exists a scalar function that I'm going to call h tilde. Associated to one, there is the other. Associated to the other, there is the one. Such that the components of the vector h, here are components, are the gradients, well, the derivatives of h with respect to phi, and the components of the velocity are minus the derivatives with respect to rho, which are Hamilton's equations.
Mhm.
So this here says those special flows, those special curves that satisfy this property reproduce Hamilton's equations. This, one can claim, is the reason for Hamilton's equations in the first place. This is amazing. It is a property of a phase space that there is a tensor such as omega that singles out certain curves as being special. These are the curves that are adapted to the geometry, to the symplectic geometry of the space.
Yeah, and the thing that we always find that the symplectic geometry is related to the count of states and therefore the entropy, and those are the curves of a flow that is preserving the count of state and preserving the entropy. That's basically my geometric intuition of this.
I wonder to what extent that entropy plays the role of, well, this is called a Hamiltonian function.
Yeah.
This is called a Hamiltonian vector field. They produce a Hamiltonian flow. But what you write here is a scalar.
Mm-hmm.
Wouldn't it be natural to try to write something like an entropy for something like the Hamiltonian function? And there's certain that could give you an interest in dynamics.
Well, the way that that we find the connection to the entropy is that whenever on a continuum, right? If you're taking an entropy, you are gonna need some volume, some measure of volume, right? And that's the measure of volume that you need to use in both in classical mechanics and in quantum mechanics to recover the Gibbs entropy and the von Neumann entropy. You have to use the volume given by the symplectic form. So that there is basically
okay, that makes sense. Symplectic forms do define a volume, which is what you're going to use.
Yeah.
And it's also interesting that in many cases, the information geometry also defines a volume. It's a geometry, right? And they coincide.
Yeah. Exactly. Over uniform distributions, the Liouville volume is the exponential of the entropy. So I'll have to show you at some point. We were basically, what we're working right now, it's we start with the notion of ensembles and just give minimal assumption of what ensembles can do, which is basically you need to be able to mix them and you need to have a topology on them so that you can talk about limits and experimental verifiability, and you have an entropy well defined. And then we're trying to basically reconstruct all of the rest, all the measure theory, all the differential geometry, all the vector space stuff, only on these assumptions. And it's amazing how much you can get. And the way that we get to measure is that one of the measures is going to be the exponential of the entropy, because it's the only sort of a function of the entropy that actually can give you a volume-like thing, that when you have this joint thing, it sums and it has nice properties. So the thing that I'm still trying to understand is how to impose this symplectic structure or Poisson structure. I'd rather have a Poisson structure for other reason. And the Poisson structure is on sort of on the let's say on the coordinates, like on the functions of the ensembles instead of being on the states. But yeah, so there's a lot of things. So the fact that you have identified here that the probability are exactly, or that the phases are exactly the conjugate of the probability, and you can do this. And this is one of the things that, okay, this works, let's say if you have the block sphere, right? This works on the shell, on the outer point. In fact, it's going to work in every a shell of constant entropy, because all the shells of constant entropy are just going to be other spheres inside, right? And so you basically will have a foliation. So the whole thing is that the state space of quantum mechanics is foliated by the entropy. And then when you pick a particular value of entropy, you're going to have a shell that is going to be a symplectic manifold. And so right now you have the right structure to put on the shell. What I want is the structure that I can put on the whole state of ensembles, such that I can write that same equation on the mixed state instead of the pure states. And I want to be able to write it in a way that works the same for classical mechanics and quantum mechanics, because I have a general formalism that both structures implement. So that's kind of why I wanted to go through this, because of course you're giving me ideas.
Okay. No, that's you're not wrong. Now, I will
I
not
agree.
I will not try to include classical mechanics and quantum mechanics in the same framework. The reason being that while classical mechanics has a well-defined symplectic structure, it doesn't have a metric structure. Quantum mechanics has both the symplectic and the metric structure. Makes a huge difference, because for the metric structure, as we're going to see in the next slide or so, the metric structure allows you to take advantage of information geometry.
Correct, but you do have it in classical mechanics on the space of distribution. You don't have it in phase space. But if you take the space of distribution, then we do recover the
It's
Fisher-Rao metric.
Sort of like a Liouville approach.
Yeah. So you basically get the Fisher-Rao metric on the space of all possible distribution. So now you're going to have both a metric, and in both cases, both classical mechanics and quantum mechanics, the way that we get the Fisher-Rao metric is basically taking the Hessian of the entropy,
of the entropy, of the relative
and putting a minus sign.
Yes, of course.
And it works the same in both cases, right? So,
but you don't get the quantum potential.
I do not know how, if and how to get the quantum potential, but again, the issue is that I'm working on the space of the full density matrix in quantum mechanics. So I do not
in quantum mechanics, yes. I don't doubt it. I do not know how to do entropic dynamics for mixed states, except by saying once you have the Schrodinger equation, nothing prevents you from mixing stuff. Right?
Yeah, I want a native way. So that's part of the thing that I need to do. So
let me
let's not get too sidetracked, because otherwise people are going to lose us.
Of course, once you have Hamilton's equations, you can actually apply the symplectic form to vectors, and that can be written in terms of Poisson brackets of the corresponding Hamiltonian functions. Right. So you can really go from vectors to Hamiltonian functions and back using formulas like this that are so beautiful. Even more, the tau derivative, the derivative of any functional along a curve, is going to be given by Poisson brackets. So here you have a tau evolution within this framework. So what's amazing about this is that I'm claiming this is quantum mechanics.
Yeah. But you're using differential
the formalism
geometry in the
is
standard
classical. Way. It's completely classical, right?
Yeah.
Right. It's just that it's completely non-classical in that these are not the coordinates of the particles. These are probabilities.
Yeah.
Very good.
The functional form for the geometry is the same, which is, as I said, it's where I want to be. I want to be able to use the same geometry for both cases, and you get the same type of equation, which are just plain derivative with some type of Poisson structure, and yeah, this is one, Ariel, again, we are too similar on this respect. Like one of the things that I always object is that it's like there is like a will, I don't even know how to describe it. Most people try always to present quantum mechanics in the most in a way that it's most different from classical mechanics, that they can't be reconciled and so on. And it's like that sometimes they go out of their way to look for things that are different, instead of to look for things that are
quantum probabilities. Yes.
Yeah.
People invent crazy things. Yes. But that's to be expected. I mean, progress requires that you do it right, and people have to try everything that's wrong, right?
Yes.
That's the nature. What is it that Churchill once said?
Yeah, Americans. Yeah.
Yeah, Americans can always be trusted to be to do the right thing after they try everything else, right?
Yeah.
Anyway, I think that also applies to physicists. Physicists will also always succeed in explaining things after they try all the wrong explanations. Anyway,
Yes, yes.
So here we have the simplex on not normalized probabilities is an n-dimensional statistical manifold. And what is absolutely remarkable about statistical manifolds is that they have a metric tensor, and that metric tensor is basically unique. Basically, what one is doing here is you take one probability distribution, you take another probability distribution. Can you distinguish them? The measure of distinguishability is going to be this metric tensor here. It's a second derivative of the entropy, of the relative entropy. And in the case of the simplex, it takes this form. The one thing that's you have freedom with this metric tensor, the one thing you have freedom, okay, yes, comment coming here, is the fact that there is an overall constant that appears here. The units of distance in this space are not determined. You can choose whatever units you want. Here, of course, with malice of forethought, I'm going to call this constant here h bar, but truly it doesn't, this is not quantum mechanics, right? It's just a constant, at least not quantum mechanics yet. And this is the metric that one gets on the statistical manifold. When you go to phase space, you have a problem because the phase space is not a statistical manifold, and therefore you have to argue a little bit more about how you assign a metric to it. So here we go for the 2n, this is n-dimensional, this is 2n-dimensional cotangent bundle. What we have is we're going to write a metric. And the reasonable assumptions I'm going to make is that if you want to figure out the distance in a displacement along the base space, it should agree with that. Furthermore, we're going to need to have what happens when you move in the direction of the phi's. And so since these guys are covectors, the appropriate coefficients, these are vectors, you get that. These are covectors, the appropriate coefficients to be the inverse. I'm going really fast on this. There is plenty that one can study and discuss. Could there be additional terms? Yes. How do you discard them? You need additional physics going on. But basically, well, those are the basic comments, the fine print, right? The Surgeon General tells you that you shouldn't smoke and all that. Yeah, there is additional stuff here. But basically, this is unique. The remarkable thing is that...
Wait a second, sorry to interject. So once I am in T star S,
yes,
I could choose even coordinates that are, a mixture. I can put anything that I can think, basically could do anything that I want. Are we saying that no matter what pair of conjugate variables we have, we are always going to have that this metric tensor applied on one side is the inverse of the one applied on the other side as long as they are conjugate?
They're covectors.
Yeah, but the G, J, K are really the inverse of each other. And when I make...
Oh, yes. Oh, yeah. Well, it's just the placing of the indices, right? If these are little vectors, these are possible gradients, things like that. They have the indices downstairs. The
fact that they have indices downstairs does not bother me. The fact that that G is the same G, just inverted, that's the thing that I find surprising.
Because this is a covector. Now, you could imagine, why not having functions here multiplying these guys here, right? Okay, that requires
No,
further
I can
thinking.
even see,
Yes.
because then you start being nonlinear, you might even have a problem. So the fact that the coefficients are the same, with just an inverse, like that you don't have an h jk, right? You don't have some other
No,
function, right?
no.
It's the same thing, just inverted.
Now,
That's the thing.
in principle, you could also have a term that mixes them with
Yeah,
the rho and the d phi term.
right.
Those terms violate time reversal symmetry. So if you want to have models that allow time reversal, then those terms have to be absent. But if you want to have time reversal, after all, physics violates time reversibility. If you want to have time reversibility, then the argument I make is the geometry of phase space is going to be this one. It allows time reversibility. If you want to violate it, you can always do that at the level of the Hamiltonian. You can always violate time reversibility at the level of the dynamics as opposed to at the level of the kinematics.
Yeah. No, this is totally interesting to me, because one of the things that I'm still puzzled about, as I said before, in the general case, I want to be able to say that in any physical theory where I have ensembles, I will have both a Riemannian metric-like thing that tells me some notion of distance, and a symplectic-like thing that tells me a notion of volumes for calculation of the entropy pulses.
Yes.
And I know that there has to be a compatibility between the two things.
Yes.
I still do not know exactly what is the compatibility between the two things is, but here you're already showing one, because you are decomposing things. Like the fact that those two things are decomposed is because those two things are the conjugate field. And so the conjugate field have a special relationship with the symplectic like structure. And then you're saying, oh, but they also have a special relationship with the geometric type structure, because you don't have the cross terms, and the terms within the same thing are the same, as just one inverse of the other.
Exactly. In other words, another very quick way to say this is when I write an upper index J and a lower index J, this is not innocent. It carries an incredible amount of baggage. And so what is the assumption that I am making here? I'm making here the assumption that whatever goes on with the phase space, I want its metric to be derived with the minimal assumptions, namely the same information geometry determines everything. So that's why the title of this talk is Derivation of Quantum Mechanics from Symplectic Geometry and Information Geometry. It's just information geometry, nothing else. This is the minimum. Anyway, so here is the length element. You have the metric for the probability part, and you have the metric for the covector part, for the momentum part. So here we have an interesting feature. Whatever those constants are, and this is the comment that I have to make here, whatever these constants are, one appears on top, the other below. Two comments here. This is a new interpretation of what h bar is. The h bar that appears in quantum mechanics is a measure, or it's a measure that weighs the different contributions of the two pieces of the phase space. If you allow h to go to 0, so that you get a classical limit, you can see immediately that this part, the metric part, goes to 0, but the part of the momenta, the phases, grows, becomes dominant. A classical limit is one in which you do not care about the information geometry of the probabilities. You just care about the information geometry of the momentum. Let me see. Yes, and of course you can write this in just in the usual way that you will write with the components of the metric tensor. and the components of the metric tensor take, oh, yes, I'm going to write it down in a second. But there is another thing that we can do here that's actually really important, which is if you have the symplectic tensor and you have a metric tensor, you can raise those indices, figure out the inverse of this tensor, and you can use that inverse tensor to raise one of these indices here. You can use the metric tensor to raise indices, yes. And when you do that, you get a mixed tensor like this. I put a minus sign for convenience, but why would we care?
It's going to be the complex structure, right?
Yes. Okay, you know the stuff. Yes, of course. Of course.
Yeah, but the people
These are
following might not, so you should explain.
Yeah. Okay, so this is what this tensor looks like when you raise indices. And what makes it interesting about this complex, about this tensor, what is interesting is that if you take the square, like I'm doing here, you get -1, minus the identity. So if you take the square of that tensor, you get -1. This is a complex structure. It's there, whether you like it or not. But it's there. There is no reason not to take advantage of it. So if you have a complex structure in your problem, it may be a good idea to choose coordinates that take advantage of the fact that there is such a structure in the system, in the geometry. So we have a complex structure, and it is a good idea to introduce complex coordinates. Why? Because if you are going to be dealing with complex, if you're going to be dealing with a system that has XY coordinates, sometimes it's good to use polar coordinates because of the symmetries of the system. Well, that's what I'm doing. Here we go. We're going to introduce complex coordinates. Rho determines the magnitude. Phi determines the phase. And this is going to be the generalized coordinate. There is here the generalized coordinate, and this is the associated canonical momentum. This means that there is a lot of fine print that goes from the previous slide to this one, right? I'm not gonna go there, but trust me, it can be done. You can do this, and when you do that, look at this. The symplectic form does not change. What that means is that what we have done in going from rho phi coordinates to the complex coordinates, what we have done is a canonical transformation. This is the definition of a canonical transformation, one that does not change the form of the symplectic form.
So basically, we're saying that the conjugate of the wave function is the complex conjugate times IH bar. That's what we're saying.
Yes.
And so these are going to satisfy Hamilton's equation.
Absolutely.
Them. They're going to have a Poisson bracket, and the Poisson bracket is going to be 1. Yeah.
The whole thing, yes. Here we go. What's the metric tensor in these coordinates? It takes this form. There is an interesting feature of this metric tensor, which is that it's constant. So what this is showing is that the whole phase space is flat. That flat space is what people call Hilbert space, but we don't know that yet.
Okay, so you're choosing a particular set of coordinates for which both the symplectic structure and the metric tensor. But wait. G is the metric tensor, but this is
in these coordinates.
Okay, so it's no, it's still symmetric because that the diagonal terms are 0. So it's not really flat, because if it were flat, I would have an identity.
But no, it's flat because this is a constant. And of course, if it is a constant, and one of the things that you could do is change coordinates further, you could change coordinates further so that you diagonalize it in this direction. Yes, you could do that.
So you're right. It's flat, so that the space is flat. I'm just not in Cartesian coordinates.
Exactly.
Yeah. Okay.
Exactly.
Okay. This the question that we had in the chat. Okay. Very, very interesting. Now, this I didn't get.
Okay. So now, how about the J tensor, the complex structure? Here's the complex structure.
Yeah.
And look at what happens if you were to apply this 2 by 2 matrix on this object here. The psi, when you multiply by j, is just multiplied by I. Well, yeah, that's what complex numbers do. When you multiply by I, you multiply by I. And how about the conjugate momentum? It gets multiplied by minus I because it's complex conjugate.
Right.
So this really starts in these coordinates. The j really starts looking like, yeah, we have complex numbers hiding in the background.
Yeah.
So we're almost done here.
By the way, is this related what you do in symplectic geometry? Sometimes you use the conjugate coordinate with complex numbers. So you have the z and the z star, right?
Okay. I'm not sure, but I think it is.
Okay. So
but by the way, the fact that here you have a metric tensor and you have a symplectic structure means that we are basically dealing with Kähler manifolds.
Right. Yeah.
Now, Kähler manifolds were invented by Kähler completely independently of quantum mechanics. And so there was absolutely no connection to quantum mechanics. I have more to say a little bit about them. But the crucial point is that at no point when Kähler was doing his stuff was there this notion that the metric structure was coming from information geometry.
Oh, yeah.
And that the information geometry of the coordinates was something that was information geometry. So no connection to probabilities, no connection to information geometry in any sense. Yeah. He was just dealing with a space with an even number of dimensions. That was all there was to it.
Yeah.
So how about now that we have Hamilton flows and we have a metric structure, how about we choose flows that not only preserve this tensor, the metric structure, but also preserve the metric tensor, preserve both. So you have these two structures in your phase space. Mm-hmm. Let's make the best of it. What are the flows that are such that they keep omega and g constant in the sense of Lie derivatives? The condition, so we want both. And this is why it's going to be Hamilton flows and Killing flows. The conditions on the Hamiltonian function that will accomplish this are remarkable. And this is my best result in all of this, because I didn't expect it, and it happened, is that the second derivatives of h with respect to the psi's vanish. The second derivatives of h with respect to the psi stars vanish.
Yeah, you get the sort of the linear elements, right?
Well, okay.
Wait, no.
Solve these differential equations, right, and impose that whatever h does, it preserves probabilities. And what you get is that the Hamiltonian is bilinear.
Yeah, it's bilinear. Yeah, okay.
Bilinear with some kernel here. And this is
right. So they're basically quadratic. So the equation of motions are linear and they're quadratic. And I intuitively, what I think you are requiring is that Gaussian states are mapped to Gaussian states.
Well, what I'm requiring is this, that the derivative of omega and g is zero.
Equivalently, right? I think that's what's going on.
This is in phase space of probabilities. So, okay, I do not know. Okay, the short answer is I do not know. It may be because, of course, whatever I do here should apply to harmonic oscillators, right?
Yeah, exactly. Yeah.
Mm-hmm. And so perhaps yes. I neither yes nor no. I invoke the fifth on this one.
Pretty the
So
same, yes.
what we have just proved is that quantum mechanics is linear, because if the Hamiltonian is quadratic in the sense bilinear, linear psi, linear in the conjugate momentum.
No, wait, then let's go back. Then I interpret the equation in a different way. Can you go back 1 second? So H here, I should think it as a function of phi m psi.
It's a scalar function in phase space. So it is a function of the coordinates and the conjugate momentum.
So right now we are,
and if you require that the second derivative of H with respect to psi here be 0, it kills it. With respect to psi prime, it kills it.
My problem is that I don't have a clear way in my head to visualize the map from the row and the what was it, theta was the conjugate of rho, and from module to phase to wave function in a way that I can understand that. Okay, fine, whatever. I'll have to think about it.
That if you try to do these things in these coordinates, in rho phi coordinates, it's awful. It is just because the metric here is constant.
Yeah, exactly.
That it allows you to simplify this tremendously. And so because G is constant, taking the Lie derivative is going to simplify. Lie derivatives have an inordinate number of terms in them. It's a huge equation. When you know that G is constant, lots of those terms disappear. The terms that remain are terms that involve this. So imposing 0 gets you there.
Okay.
So integrate this, and what you have is a Hamiltonian that is bilinear. There could be linear terms, but those violate probability conservation. So if you want your flow to preserve probabilities, they have to go away. And now we can actually write down, here is the Hamilton's equations, which can be written in this form or in the form of Poisson brackets.
Yeah, that IH bar gets swallowed by the commutator, basically. It's the thing.
Well, the IH bar is what you normally push up here, right?
Yeah.
So if you have that Hamiltonian that's bilinear, IH bar, you push it up there, and then you kill the psi star, and what you have is the linear Schrödinger equation.
That's what I was expecting when I saw the IH bar. It's gonna be the thing that allows me to go from commutators to Poisson brackets and.
I don't know that I don't know if I wrote that. I think I did. I think I have a slide with that because it's a beautiful, beautiful equation. Not mine, by the way. Anyway, so I have a remark to make here. The fact that quantum mechanics has a metric and a symplectic structure has been discovered and forgotten many times in history. The earliest,
like so many other things of quantum mechanics.
Yes, Bohm discovered that in 1952 when he was writing his papers on Bohmian mechanics. And then it was completely forgotten. It was rediscovered by Kibble in 1979, by Heslott in 1985, by Astekar and his graduate student Schilling in 1998. I learned that from Astekar and Schilling.
Okay.
Now, all of them discovered it independently. That's amazing. What none of them did was to recognize that the probabilities of quantum mechanics are classical probabilities, nothing quantum about them. They also did not associate the metric structure with information geometry. So what I have done here is sort of like invert the argument, explaining why imposing the symplectic and the metric structures allows you to derive quantum mechanics. That's it. So this is basically the what would be the first half of a talk or first third of a talk. I mean, there is.
We already are at 1 hour 20 minutes, Ariel.
It's too much. I'm so sorry. It always happens.
No, it's just that whenever we talk, we go like for hours and hours. It's always like that.
So let me give you a quick summary. entropic dynamics, and this is okay. So the issue here is I've never told you how you pick the Hamiltonian, right?
Yeah.
So that's the next half of the talk. How do you pick the Hamiltonian? How do you introduce a notion of time that resembles time? That's for some other talk. So summary: entropic dynamics is conservative in that it achieves complete ontological clarity. You know what you are talking about. This is very much the way that Einstein would have wanted it. On the other hand, probabilities are very epistemic. The probabilities reflect lack of information. So this is very much what Einstein would have wanted. Only Einstein would have thought that the particles have actually a momentum, which they don't. It is the probabilities that have momentum. The particles just have positions, that's all. So quantum mechanics in its entropic dynamics incarnation is a realistic psi-epistemic model. The particles have definite positions at all times, or the fields have definite field values at all times, but the wave function is epistemic. Entropic dynamics, on the other hand, is radically non-classical in that it denies the ontic status of dynamics. The dynamics occurs only on the epistemic level of the probabilities. That's it. There is no underlying dynamics.
Yeah, you're not evolving the position, you're evolving the probability distributions.
Of course, if you have a probability distribution, you have a probability distribution here, and tomorrow it's there, you infer that the particles must have moved. But nothing in the scheme tells you that something pushed the particles. By the way, that's what ontological models do. They assume that underlying everything, there is a lambda variable that determines the outcome of experiments. No, the lambda variables don't determine that. Ontological models violate this. Anyway, so the kinematics follows from the geometry of the phase space. The cotangent bundle gives you a symplectic structure. Information geometry gives you a metric structure, and you put the two together, you have the complex structure. Hamilton killing flows give you linear Schrodinger evolution. That's it.
Yeah, so the thing that I'm very confident, I just don't know how to do it, is that the information part is also going to give you the symplectic structure. So I just need exactly how to do that. But let's not talk about this. Let's first see if there are questions.
That's interesting.
Yeah, and I can show you. I have a paper that shows you that classical Hamiltonian mechanics is conservation of entropy, and the way that we recover or we associate, let's say, the symplectic form with the entropy is you require to have a count of states or equivalently or an entropy that it's invariant under coordinate transformation. So if you are there and you have one distribution of position and momenta, and here I have another distribution of position and momenta, and we need to be able to go back. Actually, you don't even know that there are momenta. You find out how many momenta there are by requiring that the entropy that we have on states is invariant. Yeah, it's the same for us, essentially. And the only way to do that is that if you have one set of coordinates, you need to have a conjugate set of coordinates with units that are inverse of the other, such that when you try to make areas with them, you get an invariant. And that invariant is the count of states, and the logarithm of that is the entropy. And so the symplectic structure basically comes from an application of the principle of relativity at constant time across different observers. And if you require it at observers that mix time and space, like you would typically do in relativity, then you get the extended phase space formulation of Hamiltonian mechanics. You get the time energy degrees of freedom, and that has to have a minus with respect to the other, and so you get all these things. So I'm very confident that there should be an argument just from the entropic. You're going to say, an entropic dynamic inference, and I will, make a thermodynamic argument, whatever. But the thing that the patches should still be the same. You want these entropies well defined, and you get both structures. So that's what I'm trying to find, Ariel.
Well, good
Good
luck to
luck.
you, because that would be a really nice result.
So anyway, since we are basically done an hour and a half, let's see if there are questions from the chat. If anybody has questions from the chat from Ariel, and we'll probably have to do this another time because we didn't even get to the questions that I
Now,
wanted to
now,
ask.
now you know what happens when you invite me to talk. I talk forever, right?
There's so many
Sorry about
interesting
that.
things that, geez. Anyway, yes. So we'll wait for a couple of minutes.
So what the slide that you have in there in front of you is the fact that entropic dynamics, or this approach of Hamilton killing flows, has been deployed to figure out time evolution, which is the true entropic dynamics, a notion of entropic time, and the entropic time comes with an arrow. So you have here a notion of time that.
So is your notion of entropic time similar to the Carlo Rovelli's one, or they're completely different?
Probably completely different. Yeah.
Because he also has some notion of time that comes out of the entropy.
Now, this comes from an entropic dynamics. So that's why there is an arrow of time. But one of the features about this notion of time that you may find interesting is that this is very much in the spirit of the relational approach of Julian Barbour.
Okay.
So relational quantum mechanics is one of the topics we're working on right now, but it's relational in the sense of Mach's principles and Julian Barbour, not relational in the sense of Carlo Rovelli. Yeah. So then there are a bunch of problems we tackled: measurement problem, uncertainty relations, the classical limit, spin, quantum field theory in flat space-time, quantum field theory in curved space-time, quantum field theory coupled to classical gravity. And quantum fields are scalars, so we're working also on how do you do fermions. And so there is plenty to do.
So let's go back to the question that we started. Oh, wait, there is a question. Can you clarify where you made a crucial assumption that distinguishes quantum and classical mechanics?
Basically, okay, I have two comments to make. The comment that I would like to make here is that I never derived classical mechanics. Right. I derived quantum mechanics.
Right.
How do you get classical mechanics from this? Well, you cannot get, this is the thinking that I've always had, is that no, you cannot get classical mechanics here because you don't have an information geometry in classical mechanics. Taking h bar going to 0 makes your metric tensor behave very sick. And so you don't get that. So how do you get classical mechanics? That's my second comment. You can't get it in this approach. How do you get it? Well, once you have quantum mechanics, nothing prevents you from thinking what happens when you have a mesoscopic particle that contains n particles, a mesoscopic system that contains n particles, and you ask, what is the motion of the center of mass? Yeah. When you do that, when you ask what is the motion of the center of mass, you're basically saying, I'm going to have to get rid of all the other variables in the problem, right? All the actual coordinates of the particles. And just the motion of the center of mass, that's going to behave classically because the corresponding quantum potential has a 1/n there. And so when n goes to infinity, the quantum potential disappears, and the Hamilton-Jacobi equation, you obtain the classical Hamilton-Jacobi equation.
And another way to do that much simpler is that if you take the position and the momentum of the center of mass, the commutator between that, there's going to be a 1/n. and then you take with n large, essentially the position of the center of mass become more and more commutative.
Excellent.
Like that's something that I found
Okay.
out. Like,
Okay. Of course, I'm going to scavenge that and include it in my book.
yeah. So I actually, this is one of the early things that I've done, and like you basically can show that the commutator becomes the Poisson bracket. That actually that in that case. The Poisson bracket becomes the leading term of, and the calculation is something that it's at the undergrad level. So I'll send
Yes,
it.
yes, yes.
Please scavenge it. It's a nice calculation.
Yeah, yes, yes, yes. Let me see.
Oh, we're seeing your desktop now.
I know.
Don't
That's because
reveal the secret information.
I want to fast forward. I want to fast forward to blah, blah, blah. Where is it? Where is Hilbert space? Oh, where is my Hilbert space? I lost my Hilbert space. Oh, I can't find it now. There. I guess the formula that you were talking about is something like this formula here.
We don't see we don't see the PowerPoint slide anymore. I see your desktop with there you go.
There, okay. This formula here is very interesting because
this is something deeper. This is an actual relationship between the Poisson bracket on
and the commutators
and the commutator. No, what I basically show that even just in the in the Hilbert space formulation, right?
Yeah.
If you have a commutator between two variables, and that's it's a 1 over n when then n is a parameter in the limit of large n, right? You can express that thing as a sequence of terms in an expansion in n, and the first term is the Poisson bracket.
Interesting.
So this is a little bit like when you do things with the Moyal bracket. You can show that the Poisson bracket is the first order term of the Moyal bracket, right? But what happens there is that you can sort of essentially what happens is since the commutator goes 1 over n, when you know that when you're doing you have a function of x and p, let's say, in the Poisson bracket, you can take out the derivatives and have an x and a p inside, right? If you have commutation of f of x and g of p, right? You can take those things out. And so those basically are the pieces that then become your Poisson bracket.
Okay. So what's different about this expression is that it's not an approximation. It's not
exactly. That's not an approximation. That's the real deal. That actually, I'm interested in that. Yes.
Yeah.
Exactly. Except that I want that on the space of what's it called of density matrices, not on because here you still have expressed with your psi, so it's on the pure states. So.
I think Tobias has a question.
Connor has a question.
It's Connor. Connor has a question. Yes, Connor, want to say something? You're muted.
Yeah, you should be able to talk.
Okay. Oh no, I had a comment about the classical limit. I think if you take one of the probabilities to just be centered around some ontic state, so it's like highly determined, then you recover Hamilton-Jacobi equation. Right? Like
okay, that's what happens when you do the center of mass, right?
Right. Yeah. So it'll include you just but you have to take the limit as like you keep it with some distribution, and then it takes a derivative on the Hamilton generating function, right? Or Hamilton's principal function. Hello?
Yeah.
Yeah, he's thinking.
Okay. Oh, yeah, sorry, the screen froze.
So I think you're right. Yeah, I think you're right. Yes. You take the
Yeah.
Hamilton-Jacobi equation and then you do derivatives, take gradients of it, and then things start really looking like a Newtonian equation, right?
Right.
But you're still gonna have the quantum potential. You have to somehow
Yeah. Then you
have
have
I
to make the quantum potential disappear.
I
yes,
think it
you
goes to zero though.
yeah.
Right. If you have a complete certainty.
Yeah, I think that that's correct. Yes.
Now, if you are in a pure state, the quantum potential is going to have a big contribution. So you just not going to disappear. So the way that we get the classical limit, as I was saying before, mentioning, we basically take the high entropy limit. So if you look at the space
Yeah.
of mixed states, and you go higher and higher and higher, this is clearer. If you look at things like the Wigner function and the Simi function, and if you do quantum mechanics in phase space, what you see is that you're essentially stretching phase space, and the only way to do it, let's say, when you're having a Wigner function, the zones of where your negative becomes smaller and smaller. And so the idea when
Right.
you're taking the limit of h bar going to zero, what you're basically doing, instead of going to infinite with the entropy, it's like you're rescaling the zero of the entropy lower and lower and lower. So you're basically, it's like when you do the limit in relativity, right? You can take the small velocity limit and you keep c fixed, or you take c and you put it to infinity, right? That's sort of mathematician for the group deformation. You would use c and
Yeah.
you bring it to infinity.
Well,
Here is the same thing. Instead of saying I take the entropy to infinity, I take the entropy of the pure state and I bring it to minus infinity. And that's the corresponding h bar going to zero. That's what we show in the paper. It's now under review, and we need the two. But
well,
the math, it's nice because it's not that complicated in the end. You're basically doing a stretching operation of phase space because that's the only way that you can increase entropy of all mixed states at the same rate.
I think the difference here is that like we're picking a ontic uh space first. Like if it was positions, you just say, oh, it's just probabilities over positions, not probabilities over positions and momenta, like you would in a Wigner function.
Right.
Because are you basically saying like you're considering both of them as ontic at the same time? Because then you get the problems with negative probabilities and
So I
uh
don't, let's say, I essentially get rid of what is ontic and what is not. So my
okay.
purpose, going back to what Ariel had, right? The sort of the mathematical formulation and the interpretation, right? What we want to try to do is to have such a minimal interpretation that it's on things that every interpretation has to agree because they are the things that are directly connected to experiment. So we basically are
Right.
completely agnostic on what is ontic and what is not ontic. The thing that we know is that we're going to have ensembles because ensembles are going to be the thing that we go and prepare in the lab and make measurements on and so on.
Right. I
What
mean,
are the... Yeah, go ahead.
oh, sorry. I mean, I've had discussions with Dr. Caticha on this about Wigner functions and stuff. And I do think it's interesting how it gets you the different limits and answers, but I do agree with him that a negative probability has problems for interpretation, right? So like just writing the Wigner
I'm
entropy, it's
right
kind of
now making a YouTube video on negative probability. Just
okay,
right
okay.
now.
So I'm of the opinion that negative probabilities strictly on their own, they don't really make sense. They don't.
Correct.
It's not meaningful by themselves. But I think it's interesting how using them like it conspires in certain ways to get you the right answers. But I don't know.
So,
Do you have like your own what's like okay, if just forget about quantum mechanics, if you just have some system and you try to like do contradictory constraints, you get negative probabilities. Like what is your interpretation of that?
they're not probabilities.
Okay,
So the idea is that any ensemble space you can show that it's a convex subset of a vector space.
right.
Okay. Now, any vector space can have affine coordinates. So if I have a plane, which is a two-dimensional vector space, I pick 3 points, and I can have affine coordinates. What are affine coordinates? Are linear combinations where the sum of the coefficient is 1.
Right.
Okay, so you pick the origin, you pick two other points apart from the origin. Everything else is a convex combination of those 3 points. Okay, so if you have your block sphere, right?
Yeah.
You can take 4 points on the block sphere, right? And if you connect those 4 points, you're going to have a 4-dimensional simplex, a 3-dimensional simplex, or a 4 simplex. I never remember if the simplex is the dimensionality of the vector space or the number of points. But anyway, you're going to have a tetrahedron, which is a simplex, right? And inside the tetrahedron, right, all the points inside the tetrahedron are also going to be inside the block sphere. Those are going to be probability are going to be convex combinations. So you can sort of interpret it with probability, but they're not probability at all. They're just convex combination because everything sums to 1 and it's greater or equal to 0. Now, the problem is that, of course, the block ball is bigger than the tetrahedron. So you have some points that are outside the tetrahedron. Well, those points you can reach with an affine combination, with relaxing the fact that the coefficient has to be greater or equal to 0. They can be negative. Now you have, you can take 4 points in the block sphere and have coordinates that get all the points of the block sphere by making an affine combination. And because it's an affine combination, any linear operator in the Hilbert space, and therefore in the projective space, and therefore in the space of the mixture, is linear with respect to the representation of your affine combination. Right? So it's very powerful and very useful because now you can make all your calculations in terms of these coordinates and things work very, very nicely. But it's just another representation. It's not that the fact that the sum probability is negative tells you something physical, because you could also take the tetrahedron and rotate it inside the sphere. And now which points require a negative coefficient have changed. So there is nothing that is a fact of the matter that some points have negative probability or not. It depends on the coordinates that you have chosen for your affine combination.
Well, I mean, I'm not necessarily just thinking about the physics here. I'm just thinking in terms of like, for classical probability theory, right? If you define entropies and you set these constraints, right, you can use it to reason about any type of problem, right? You can say, given this information, I'm going to set this constraint. What is the least assumptions I get for this probability distribution? Like mathematically, yeah, you can extend it so that you can get regions that would be in like where you have negative probabilities and a negative information metric or negative determinant. But the issue I have is
you can't.
Right. Oh, you can't?
No, you can't do entropy maximization with the Wigner function. You're just going to make a mess.
I mean, no, you can for a certain state. Like you can do it for Bell states where it's like, okay, here's you have like 3 different Booleans and you write the entropy, and then you can say, I want to get the correlations that we find in quantum mechanics. And if you do that, you'll get the negative regions, right? You'll say like, oh, this joint probability has to be negative, right?
Yeah, but that's a different problem, and you're probably asking for a particular. What I'm saying is that if you want to do entropy maximization, right?
Right.
And you want to do it on the Wigner function, you do not know how to do it because there is no simple way to express the von Neumann entropy in terms of the Wigner function. If you have it, please give it to me because I've been looking for like 3 years. And
well, can't you just write the Wigner entropy? You just write W and then log W and then integrate over.
Oh, that's the Shannon entropy calculated on the Wigner function. That it's not the von Neumann entropy.
No, I know it's not the von Neumann entropy, but you can just find constraints that'll get you the right. You can find constraints basically that corresponds to what the quantum states would be.
There are some version of the Renyi entropy that, if I understand correctly, they carry over. But
Right.
in general, it's
Right. It's the interpretation is not clear, but
well, it's not even interpretation. If you want to do statistical mechanics, you better use the better maximize the von Neumann entropy because that's the one that
right.
corresponds to. So if you don't know how to do that, you can't do statistical mechanics. And
Mm,
so I think what I'm trying to say is that every uh, mathematical representation of your physics is going to be good for some things, but it might be horribly bad for others. So if you're doing
yeah.
quantum optics and quantum tomography and that type of stuff, the Wigner function is extremely useful. You can do a lot of things that would be a lot harder to do in terms of the standard vector Hilbert space formulation, right? But the issue is that other things, if you're doing statistical mechanics, is going to be a lot
Well,
harder.
well, even the von Neumann entropy, I mean, if we take like a strictly like Gibbs entropy, just saying that okay, it's the probabilities log probabilities, right? That doesn't correspond to von Neumann entropy. So,
Mhm.
right, it's zero for pure states. So then
No, but it's
it's not
even
a
worse than that because you have a negative probability, so you can't even define
right.
like it just doesn't work.
Yeah,
And you can only do it, let's say, in Gaussian states. But then again, the entropy of the Gaussian states, because they all have a positive or non-negative Wigner function, still it's not going to correspond to the von Neumann entropy in general, even for those states. So you
yeah.
really can't do it.
I don't know. Didn't von Neumann say not to take his entropy too seriously? Maybe he's maybe somebody said that. Because
But
I don't know, does it like really correspond to an entropy? Because I mean, if we're taking the point of view that the entropy it measures a degree of uncertainty, right? Then you still have uncertainty in a pure state.
to me, the entropy this is where we have a little bit of a different
Yeah,
starting point between me and Ariel. For me, the entropy that matters is the one that it comes from thermodynamics, and it's going to be the one that measures the variability of the elements within a distribution. In basically here,
yeah,
it's the variability of the elements within an ensemble. And I
right.
can prove that there is one and only one. Like
Yeah,
I have in the framework, we have like three very minimal assumptions that you have to require on this entropy
right.
function, and it picks out the Shannon entropy without knowing whether you are in a quantum state or in a quantum state space or a classical space. Like, there is basically only that. When you take two ensembles and you mix them up, there is going to be an upper bound that the entropy can get during mixing, and that upper bound is going to be given by the Shannon entropy. There is no
Yeah,
other formula.
yeah. I believe you, but but
I have to say that there is an approach to the von Neumann entropy and to the quantum relative entropy, the Umegaki entropy. There is an approach that's very similar to what one uses to derive the Shannon entropy and the relative entropy in the more classical version. It has to do with ranking probability distributions. And if you decide, instead of ranking probability distributions, you decide to rank density matrices, what you get is the von Neumann entropy, you get the Umegaki entropy, and all of those things.
Ariel, just one second. Could you like remove your share so that we can see your face better in?
Didn't I remove it?
No, you removed the PowerPoint, but you didn't stop sharing your screen.
Oh, I see. What do I have to do here? Where do I go? My screen.
Can I
No,
do it for you? I don't think I can do it for you.
no. Let me.
Stop sharing.
I thought I had done that.
You know what? I can replace your share with my screen for a second and then stop sharing. There.
oh, there you go.
Is that better?
Yeah, I've done it. Don't worry. So
Okay, all right.
sorry about interrupting. You were saying.
Oh no, what I was saying is that this is the work of Kevin Van Slet. It's in my book for the classical probability case, and eventually I'll add the density matrix things. The idea here is that you want to rank probability distributions and you want to rank them in such a way that when you pick the best, you just, you have them ranked, and so you pick the one that maximizes an entropy, right? And the entropy that you have to maximize is going to be relative entropy in the case of probability distributions, and it's going to be the Umegaki relative entropy, which is generalizes Shannon von Neumann in the case of density matrices. So the whole thing works nicely.
Does that, well,
and it applies to statistical mechanics, whether classical or quantum. It works. Yeah. Oh, you were saying, Connor?
Oh yeah, I guess my issue with the von Neumann entropy specifically is that it treats quantum probabilities and classical probabilities very distinctly, right? Does this one measure both somehow?
Oh, this is all, the probabilities are probabilities.
Yeah.
A density matrix is something else. It's a different structure. So the probabilities here are completely universal, the same probabilities that you would use in both cases.
Yeah, right. I mean, I think that's like similar-ish to what Wigner entropy tries to do, but right, of course, it has the problems with the negative regions. Right, because it still has like a minimum value, right? Because you can't from the uncertainty principle.
Well, so, that's why I don't like the Wigner approach.
Yeah.
No, I repeat the thing. It's very simple. You can't use the Shannon entropy on the Wigner function. The only Wigner states that are non-zero, the only pure states that corresponds to Wigner functions that are non-zero are the Gaussians. There are no other things. So even if you say, oh, I want to define it, you would only have it for the Gaussian. Not very useful.
Yeah. I thought Wigner functions, they're always positive definite for ground states, right? So you don't have the issue there.
No. They're only positive definite for Gaussians. The Gaussian states are the only pure states that have a Wigner function that is non-negative. The fact, so when you do quantum optics, they always work with Gaussian states. That's one of the reasons why they like the Wigner function so much. And they take the fact that the absence of negative entropy as being one of their definition of classicality. They sort of define it like that because for their purposes it makes sense. Because from their perspective, the Wigner function looks classical, so it's a classical state, but they're not. Like the pure states are definitely not classical. And so if you take an harmonic oscillator, well, the pure state is a Gaussian, good, you're safe. But for any other system, it's not going to be the case. And so when you are doing quantum statistical mechanics, that you have a mixed state and it's going to be whatever it is, Wigner function is in general not going to be non-negative when you do entropy maximization.
So it can be negative even with zero phase.
Yeah.
Okay.
Yeah, when you're doing the Wigner function, right, you're multiplying with an exponential with all the possible phases, right? So even if you start with no phase, well, you're going to get a lot of phases during the integration. Yeah, as I said, like to me, they are a nice mathematical representation because they are linear with respect to the mixtures, right? And therefore, they're also linear with respect to all the Hermitian operators. So, so you can do things that are nicer than what you do, for example. Man, like the space of density operators, like it's really a pain to work with. I mean,
I mean, that's one issue that I had with when you just consider like classical transition probabilities, like a Wiener process, right? you can't have something that's linear in the probabilities, but then also takes into account like wave function unitary evolution, right? You can't be linear in the thing and the thing squared, right? At the same time. But I guess you can for like a phase space formulation.
Well, I wouldn't know, for example, so the other things that becomes a lot more complicated. So the time evolution, like
the
the
Moyle
Schrödinger equation,
brackets.
that becomes that becomes a complete mess, right?
Yeah.
So there are some things that I think remain similar. If you make like the overlap between two functions, like if you're making the inner product between the two mixed state, I think it should be decent but again, I'm not an expert in these things. But there's some things, as I said, some things become harder. Like time evolution becomes a lot harder, for example.
Right. Yeah, it's pick your poison, I guess.
Yep, pick your point.
No. All right, thank
Any
you.
other question from the chat? Otherwise, since it's been 2 hours, so maybe we can close the live.
Adjourn.
All right. Okay, so let's thank Ariel, and yeah, I'd be inclined to do it again at some point so that we can talk about all the other things that I had I wanted to ask you and I didn't get the chance. And again, if anybody is interested, please do let me know in the comment if you want another live, because otherwise I can talk to this guy by myself and drill him a lot faster. So thank you again.
Thank you very much for the invitation. This was a pleasure.
Thank you, guys. So I think it was fun, right? I think it worked out well. So, and we'll see how many people will watch this and how many questions we'll get. So I'll do another live. See you next week, and bye, everybody. There we go. Stream finished.